This is Dr. Wood. This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. And in this lecture, we're going to look at learning objective 2.4.1 that looks at curvilinear motion in Cartesian vector coordinate systems. So in the Cartesian vector coordinate system, we have something like this, where the position is defined in terms of its x and y components. So if we were to sketch that real quickly, we would have our x and our y, and our r would be out here, right? To find some point. Now, we said in our previous lecture on curvilinear motion that if we wanted to go from position to velocity, we'd have to take the derivative with respect to time. And it turns out that when you do that, you have to use the product rule, and you have to take the derivative of both the x component and the I, or the y component and the j. Now, it turns out that those unit vectors I and j don't change. So when we take the derivative, they end up being 0. This makes Cartesian vector coordinates easy to work with because each coordinate direction, the kinematic properties for each coordinate direction are going to be independent and rectilinear. So what that means is that I could use my rectilinear motion knowledge to analyze the x component and not worry about the y component. Then I can use my rectilinear kinematic property equations to analyze the y without worrying about the x. And so this becomes a fantastic tool. It's on page 77 of your FU reference handbook under Cartesian coordinates. This becomes a fantastic tool for two very specific types of problems. So we're going to use this when we think about relative motion so that's a later lecture, and projectile motion. Got to spell it right. Projectile motion. So Cartesian motion is great for projectile motion. Now the reason that this is true is that typically what we'll do is we'll set up our x-axis as the horizontal axis and our y-axis as our vertical axis. And so when we do that, we can think about what's happening in the y direction independent of what's happening in the x direction. So if we were to go and explore that projectile motion equations, we would look in our FE reference handbook. It turns out these equations are already worked out. Again, this is a special case of Cartesian motion. Projectile motion. It's on page 79 of your FE reference handbook, and it starts with acceleration. Okay. Now, when we think about this acceleration, we can really break this into our two components. Like we said, we would have our horizontal component. We call that x, right? And our vertical component, y. I misspelled vertical, didn't I? Yep. Good at math, not as good at spelling. Vertical component in the y direction. And if we think about what's happening in the y direction when we shoot an object, so in a minute, we're going to switch over to a video of me playing with a Nerf gun, and I'm going to shoot the Nerf gun. And if we think about what's happening is that projectile fires in the y direction, gravity is acting. And so our acceleration in the y direction is going to be equal to negative g. Now, when I have g here, I'm thinking only of the magnitude of the acceleration due to gravity. So this is 9.81 meters per second squared for SI units, or 32.2 meters per second, or feet per second squared, excuse me, for US customary units. And the negative indicates that it's pointing down. So our typical assumption here is, again, that x is going to be horizontal and that y is going to be 0. When we think about this neglecting air friction, which might not be the best thing to do, but remember what we're doing is we're looking at reality, something like a let's say a Nerf dart flying through the air, and we're going to build a mental model that says what matters is gravity and wind resistance, but we might neglect that wind resistance because at the end of the day, we're playing with a child's toy. It's not really worth the effort, and we can make a simplifying assumption for our engineering and math model that we're looking at here. Now, when we've done this, I hope something is firing in your brain from our lectures together, which is to say that we already have special rectilinear tools for dealing with stuff when acceleration is equal to 0 and when acceleration is equal to a constant. And so we can use those equations in this case to figure out what our velocity is. So in the horizontal direction, our initial velocity in the x direction isn't going to change. It's going to be constant, right? So it's just going to be a constant. But in the vertical direction, our Vy as a function of time is going to be equal to this equation here, where we'd have Ay, t minus t naught, so the change in time, plus the initial y velocity component. Now, that all looks fine and dandy. Your FE reference handbook draws a little picture like this to help us think this through, where this is our initial velocity at some angle. We have our y and our x, and of course it could be broken down into its v naught x and v naught y components, and we could use that using knowledge of that angle, that initial angle there, theta, measured up from the x-axis. That up from the x-axis is important to make these equations work. So if we look at what's in your FE reference handbook, what they end up saying, so this is Vx is always going to be equal to Vx naught, but Vx naught is just equal to V naught times the, let's see, whoops, I flipped my signs here. Vx naught is going to be equal to V naught times the cosine of theta. And Vy is going to be equal to negative g delta t plus V naught sine of theta. Something like that. And so those are the equations you should see in your FE reference handbook, or something very much like them. If we wanted to know the total velocity at any given point, we'd have to do the square root of the sum of the squares of our Vx and our Vy. So that's velocity. Now when we think about position, again, we can take another notch up. We know that when acceleration is equal to 0, the position, some location x, is going to be equal to the Vx naught times t minus t naught plus the initial x position, like so, and our y location is going to be equal to 1/2 ay t minus t naught squared plus Vy naught t minus t naught plus y naught, like so. So this is just straight up using those kinematic relationship equations we had for acceleration equal to 0, constant position, and the acceleration equal to a constant. We would have an equation for our velocity and an equation for our position. Now, if we substitute in these sines and cosines, these things that we already know here, these equations will change just a little bit. We'd get V naught delta t cosine theta plus x naught, and y is equal to minus 1/2 g delta t squared plus Vy naught delta t, Vy naught we know, V naught delta t sine of theta plus y naught. And so when we're looking at projectile motion, we're going to have 1, 2, 3, 4, 5, 6 equations that we can work with because we're able to evaluate our x component as independent and rectilinear and our y component as independent and rectilinear. And using those equations together, we'll be able to solve the problem. Now, typically, I will say that we assume that our initial t value is 0, so that delta t might go to a t, the way you see it in your FE reference handbook. And so I just make sure that that's in your FE reference handbook. These equations here, I'll put a little star by them. Know where to find them on page 79 of your FE reference handbook. And keep in mind this little sketch here. I'm going to go take a video of me playing with a Nerf gun so that we can solve that problem in class. So here I have my Nerf gun and my tape measure laid out, and I'm going to fire 9 darts from my Nerf gun. It's battery powered, so I won't have to cock it or anything. I'm going to start off with an initial elevation of 3 feet. And so we need to know our initial elevation. So the dart's going to fall 3 feet. And then we also need to know the initial angle. We could shoot up or down and measure with the protractor, but in this case, I'm just going to fire horizontally. And so as horizontal as I can get it, 3 feet off the ground, and I'm going to start shooting darts. I'm paying attention to where they land at first, not so much where they land after they bounce. With the grass, most of the darts are bouncing straight up and then falling back down where they land. And so that is all the darts. There's my cluster of darts. I've got a couple that bounced and landed farther away, but I was watching and they mostly hit here. So if I look at my tape measure, this tape measure measures in engineering units, so tenths of feet, and we're right at 16 foot for our range. Back inside from doing our projectile motion test with our Nerf gun, right? And I thought I'd set up our problem for our class time together. So when we went outside, we established some initial things. So first off, if we look at our equations for projectile motion, we didn't measure it, but we are assuming that air resistance is negligible. Now for a Nerf gun, that's probably not true, but close enough for children's toys. We believe gravity is working, so that's a pretty safe assumption as well. And so our mental model should be pretty strong. Now, one of the things that we measured was we measured this initial angle. And when we're outside, we said, let's just fire it horizontal. And that's going to simplify some things, right? So if theta is equal to 0, what's cosine theta equal to? Well, cosine of 0 is equal to 1. So that's going to simplify these equations a fair amount. And if theta is equal to 0. What's sine of 0? Well, the sine of 0 is 0. So that's going to simplify these equations a fair amount. And so we know that. We also know that our change in x, so that's going to be x minus x naught, was equal to 16 feet. That's what we measured with the tape measure. And we said that our initial elevation, delta y, so y minus y naught, was going to be equal, our change in elevation was equal to 3 feet, but that's negative 3 feet. So we can put our signs on there like so. And so that's the initial conditions that we were able to measure. And believe it or not, from that, we can calculate our initial velocity. And so the initial velocity is the thing, say we would want to know the initial and final velocities. This equation is not going to help us. This one's self-evident. This equation is also self-evident, so V naught's equal to V naught, so not helpful there. This would be helpful if we knew V naught. So if we look at these things, we'd have 1, 2, and 3 unknowns in that equation. We don't know time and we don't know the velocity. But if we look at this equation down here, we know the final position, or at least position minus x naught, right? 16 feet. We still don't know time, but we do know, and we're aiming to find that velocity there. So that's 2 equations with 3 unknowns, right? Life's looking pretty good. And then here, In our y direction, we could look at this. Well, we still don't know time, and we don't know the initial velocity, but we do know gravity is working, and we know my y minus y naught, -3 feet. And so it turns out we can use these two equations to solve for the unknowns delta t and v naught. We'll do that in class together when we meet together, but if you want to get a jump start on it, you can actually solve that on your own. So I look forward to seeing you in class. You'll have an exam question that's very much like this. So this is a problem worth mastering as we go forward. All right, I look forward to seeing you in class so that we can find both our initial velocity, magnitude and direction, and our impact velocity, magnitude and direction. So I look forward to seeing you in class. Take care. Thanks.